Hello, welcome to this lecture on hashing. In this lecture, we're going to talk about hashing and what it is, and some of the uses that it has within computer science and in security. Now, you may remember from previous lectures that in hashing, we take an arbitrary message and we compute a fixed length hash. Now, sometimes we call that hash a message digest. So you may see a hash or message digest used if you're reading about this. Hashing is used outside of security as well. In fact, the principles behind hashing are used in a lot of different areas of computer science, and they're used in a lot of different systems. So out of all the things that we talk about in this course, hashing is the one that you may see the most outside of security applications. So while any security hash function can be used for a lot of other purposes, not every other type of hash function can be used for security. So what we're going to talk about today are specifically called cryptographic hash functions. And that just means that they were designed with some extra mathematical properties in place that make them safe to use for security and cryptographic purposes. Let's look at an example. So we have some arbitrary amount of data. It doesn't matter how much it is. It could be 1 bit, it could be 1 million bits, it could be a terabyte. It doesn't matter. Any amount of data. And we feed that into our hash function. In this case, I've just picked one called SHA-1. That's just an actual hash function. And what we get out, with the example of SHA-1, is a fixed length 160-bit hash. So it doesn't matter how much data you put in, you always get out 160 bits. So if I put in 10 bits here, I get 160 out. If it's 100 bits, I get 160 out. If it's 1,000 bits, I get 160 out. So it doesn't matter how many bits I put in, I always get 160 bits. But this output will be very different depending on the input. So as a sample of how hashing is used in, say, like a programming language, I just picked Python because it's usually pretty easy to understand. In this case, I just created an instance of a hash function method, hash function object. I added some text to it, and then I just said create a digest, and print it out. And traditionally, when we print out hashes, we print them out in hexadecimal. So let's look at some properties of a secure hash function. So if we're going to use a hash function for security, it has to have some special properties. The first is called pre-image resistance, or it needs to be one way. And what that means is that it's infeasible to determine the original message if you're given a hash. So it's infeasible to determine M from a hash of M. So if I hash something and I give you the hash, you're not able to take that hash and go backwards to find a message that has that hash. Now the next property is called second pre-image resistance. And in second pre-image resistance, we say that given M1, it's infeasible to find M2 such that the hash of M1 equals the hash of M2. So if I give you a specific message, you're not able to find another message that has the same hash as the one that I gave you. And the third property of a secure hash function is called collision resistance. And this says that you can't find any M1, M2 such that the hash of M1 equals the hash of M2. So at this point, a lot of people stop and they say, well, wait, what's the difference between 2 and 3? In both cases, you're trying to find two messages that have the same hash. And you're right. In both cases, we're trying to find two messages that have the same hash. But in second pre-image resistance, you're given a specific message, M1, and told to find another message with that hash. In collision resistance, you're told to find any two messages that have the same hash. So from an attacker's perspective, if an attacker is trying to break these properties, it's easier for an attacker to break collision resistance because collision resistance can be broken with any two messages, whereas second pre-image resistance, you have to find another message with the same hash to a specifically given one. So it's the difference between a specifically given message you have to match and finding any two messages with hashes that match. So if I were going to break pre-image resistance, what would I need to do? And remember that pre-image resistance says that given a hash, find a message with that hash. Well, I mean, the brute force approach, brute force meaning I just keep trying and testing and seeing if I get it. In a brute force approach, I would just pick a message, hash it, and compare it to the hash that I have. If they match, then yay, I found a message with that hash. If they don't match, then I pick another message, hash it, and compare it to the hash that I have. I would just keep picking random messages and hashing them until I find one that matches the message that I chose. Well, how long would this take? Well, in the best case, my first guess would be correct. I would be like the luckiest person in the universe, and I would just pick a random message and hash it, and it would happen to hash to the exact same thing as the hash that I'm trying to match. I would be incredibly lucky. In fact, the chances of that happening are so small it's not even worth talking about. But that would be the best case. In the worst case, I would be the unluckiest person in the universe, and I would keep picking random messages and hashing them, and I would find every other possible hash first. And then lastly, I would find the one that I'm looking for. So in my best case, I get it in one. In my worst case, I try every other possible hash. And so if I'm dealing with, say, a 128-bit hash, just pick that number for fun. So if I'm dealing with a 128-bit hash, then there are 2 to the 128 possible different hashes. And if I find all of the others first, well then I would find my answer at 2 to the 128 minus 1. In the average case, I would hit somewhere in the middle. Not somewhere in the middle. In the average case, I would hit right at the middle. I would find it halfway through. So that would just be the worst case, more or less, divided by 2. So I would get about 2 to the 127, which at first glance, you pause and you say, wait, if you're dividing this big number by 2, that should make it substantially smaller. And it does, but remember, we're dealing with powers of 2. So dividing 2 to the 128 by 2 only gets me 2 to the 127, which is still a really big number. So how big of a number is 2 to the 127? It's about 1.7 times 10 to the 38. So that's like a 1 with 38 zeros after it. That's an extremely large number. If you were to write a really fast computer program to try this approach, which is pick a message, hash it, check it, pick a message, hash it, check it, it would take you an incredibly large amount of time before you would finally break the hash. So this is really not feasible for someone to do. It would take way, way, way too long. So how about if I need to break second pre-image resistance? And if you remember, second pre-image resistance says that given M1, I need to find an M2 such that the hash of M1 equals the hash of M2. So in pre-image resistance, I was given a hash. In second pre-image resistance, I'm given the message. Well, if you're going to apply the brute force approach, you would use the exact same approach we did for pre-image resistance, actually. I would simply hash the message, and then I would perform a brute force attack against that hash to find another message with that hash. So the attack would be basically the same in the brute force approach. Now, in collision resistance, remember in collision resistance, we're trying to find any two messages with the same hash. When we're trying to break collision resistance, things get a lot more complicated. So in order to understand how you could break collision resistance on a hash function, you need to learn a part of probability called the birthday paradox. To explain it, I'm going to use an analogy I call the birthday collision. So the birthday collision is assuming that all birthdays are equally likely. How many people do I need to get together in a room before 2 of them have the same birthday? And if 2 people do have the same birthday in a room, I'm going to call that a birthday collision. So that's the problem. How many people do I need to get in a room before any 2 of them have the same birthday? Now this problem is distinct from a related but different problem, which is how many people do I need to get in a room before one of them has my birthday? And I hope you can see the difference there. In the latter case, I'm trying to match someone else to a specific birthday, mine. But in this case, I'm just trying to have any 2 people with the same birthday. So those are 2 different problems, even though they sound disturbingly similar. But remember, here, any 2 people with the same birthday. Well, the rule of thumb, and we get this from what's called the birthday paradox, if you do the statistics out, the rule of thumb is that if there are n different possibilities of something, then you need square root of n randomly chosen items in order to have a 50% chance of a collision. So what does that mean for the birthday collision idea? Well, if there are 365 different possibilities of birthdays, well, the square root of 365 is about 23. So the answer to our birthday collision question is that we would need about 23 random people before we have a 50% chance that 2 of them have the same birthday. And that number is actually fairly low. Most people would think it would be higher. Just intuitively you think, how many people do I need before they have the same birthday? I don't know, hundreds? But really, it's only about 23. In fact, if you get 23 people together in a room, you have about a 50% chance of a birthday collision. Now, for birthdays, this doesn't necessarily hold because the truth is that birthdays are not equally likely to happen on every day of the year. Some months are more likely to have birthdays than others, et cetera, but hopefully it's a good analogy to help you understand the birthday paradox. So this is the birthday paradox. If there are n different possibilities, then square root of n is all I need to have before there's a 50% chance that two of them are the same. So how does this apply to hashing? Well, recall that collision resistance says that I can't find any M1 or M2 such that the hash of M1 equals the hash of M2. Well, if I were to just start generating hashes and storing them, so I pick a random message, hash it, pick a random message, hash it, and I keep track of all of the hashes, how many hashes do I need to collect before I get a collision? It's almost the exact same question as the birthday collision question. It's just we're dealing with hashes instead of birthdays. Well, for a 128-bit hash, there are 2 to the 128 possible hashes. So if I apply the birthday paradox, well then the square root of 2 to the 128 is 2 to the 64. So that's how many hashes I would need. And that's still a big number, but this means that the strength is similar to breaking pre-image resistance for a 64-bit hash function. So I can break collision resistance significantly easier than pre-image resistance, for example, because the birthday paradox brings down this 2 to the 128 power and really ends up reducing it to something as small as a 2 to the 64 power. Okay, so let's talk about some examples of real hash functions. So the first one I want to talk about is called MD5. And MD5 produces a 128-bit hash, but MD5 has some mathematical weaknesses that smart cryptographer people have analyzed it, and they found that they can actually find collisions, so break collision resistance, in only storing about 2 to the 21 hashes, which is significantly less than the 2 to the 64 that it would be in theory. So that's because they've analyzed the algorithm and found mathematical weaknesses in it. SHA-1 is another real hash function, and it's a 160-bit hash. And as cryptographers have analyzed it, they found that collisions can be found in about 2 to the 61 hashes. The theoretical limit for finding collisions would be about 2 to the 80, but they can find it 2 to the 61. SHA-2, which was a modified version of SHA-1, is actually 4 different hash functions with different size outputs. So SHA-224 is, a hash function that produces a 224-bit output. SHA-256 produces a 256-bit output, and so on. The SHA-2 series of hash functions, there are very, very minor attacks, but overall these are still considered good. We don't know of any attacks against collision resistance that significantly reduce the computation time. So that's good. These are more commonly what people will be using today if they want a good secure hash function. And then there's an even newer hash function called SHA-3. You might notice the trend in the naming, called SHA-3. That was just chosen now as a new standard for NIST, which is the National Institute of Standards in the United States. And it's new enough that there's no known attacks. People have been analyzing it, but they've only been analyzing it for a few years. And so at this point, it's considered very good. But you want to wait until people have spent enough time with it. But it is probably very good. So in practice today, when designing new systems, most people are going to either use one of the SHA-2 functions or the SHA-3 function, because both MD5 and SHA-1 have potential attacks that reduce its collision resistance. Now, finding a hash collision in 2 to the 61 is not incredibly feasible. That could be difficult. But finding one in 2 to the 21, that's very feasible. You could write a computer program to do that in a reasonable amount of time. So let's talk about some applications of hash functions. So some things that people use hash functions for is to detect errors in file transfers. So for example, BitTorrent uses hashes to detect if there was an error in some of the blocks of data that it retrieves from peers. Another use of hash functions is something called a message authentication code, which is a way that two people who share a key can basically use a hash with a key in order to guarantee the integrity of something. Another good usage of hash functions is in password storage, when an application is storing the passwords of users, specifically server-side applications. Let's talk about each of these. Okay, so for the file transmission idea of guaranteeing that the file hasn't been corrupted, Hash functions are used in a really simple way. What you do is the distributor, the person you're going to download the file from, takes the file, however big it is, and they run it through a hash function. You get out this hash value here, and they just put it on the website. Sometimes you'll see this when you download files. You'll see here's the file and here's its hash. And you may have wondered, well, what's the hash for? The hash is for verifying that when you download the file, it wasn't corrupted. Because if the user downloads the file and the file is received correctly, well then when the user hashes that file using the same hashing algorithm that the distributor did, the hashes will match. So the hash that the user downloaded from the distributor and the hash that they generated from the file will match because they were generated from the same data. So same data into the hash function gets the same data out. But if there was any error during the download, even 1 bit, if even 1 bit is different, then after I hash it, I'll get a completely different looking hash. So if 1 bit changes here, the output will be substantially different. Just like block ciphers. You may remember that in a block cipher, if 1 bit of the plaintext changes, the ciphertext changes significantly in a way that's indistinguishable from random. The same is true for hash functions. So if there's any bit errors at all in the download, then the hashes won't match and you'll be able to detect. So it's a nice way to verify that a file hasn't been inadvertently corrupted during a download. So another application of hash functions is called a message authentication code. And this is basically hashing with a key. The goal is to create a hash that can only be created or verified by someone who has the key. So if you and I share a key, and I want to send you a message, and I want you to be able to verify that the message came from me and hasn't been changed by anyone in the middle, then we could use this. We could use a message authentication code to hash the file with the key, share the hash with each other, and then we could detect if anyone altered it. There are different techniques. The simple thing is I could just say, well, I'm going to hash the message, and on the end of the message, I'm just going to add the key, right? So whatever the secret key is just gets added to the end, and then I hash that whole chunk, and I get a hash. But this is bad because of how some hash functions are designed. Just putting the key on the end is not always the best approach. I could put the key at the beginning. Well, this is better because hash function designs don't necessarily cause this to be a problem. But some research has been done to say that there are other better ways to do it. I could put it on both sides. I could put the key at the beginning and the end, which would be better still. But the best way to do it, and the way that's provably good, is this actually. So we hash first with the key at the beginning of the message, and then we hash again with the key at the beginning of that hash. So we do the hash twice with the key at the beginning both times. And this is provably good. And provably meaning that someone has verified mathematically with formal proofs that this is sufficient for guaranteeing the integrity of the message. So this is the best way to do it, provably. Someone has verified that. But it's also slower because you're doing the hash twice. Now another application that people use for hash functions is password storage. So if you design an application that stores passwords, usually like a web application or some sort of server, you don't want to store them in plain text. And the reason is that if anyone breaks into your server that's hosting this application and they steal your database or your password file, well then they have all the passwords of all of your users. And that's a horrible thing because the users may reuse passwords to other systems, or the attacker then just has all the passwords for your system. It's just not a good situation. So instead, you should be storing hashes of the passwords instead of the passwords themselves. And I want to make a note that if you're really going to do this, you don't just store hashes. You do something specific with a hash that adds some security. So if you ever need to do this, just go look up password-based key derivation functions, or PBKDF. Just type that into Google. You'll find all sorts of useful reading if you really do need to store passwords. But the core of that technology is just using hashing. So as an example, here's, say, a password file that a system might use. And what we would have is say, okay, well, here's the user's account name. It's just their email address. And here's a hash of their password. So instead of storing their actual password, you just store a hash. And that's useful and helpful. And then if an attacker breaks in, they don't get the password, they get the hash. And if the attacker wants to get the original password, he has to brute force it. He has to break pre-image resistance by randomly not randomly, but by hashing potential passwords and comparing to this hash. So it significantly increases the work an attacker has to do to get the passwords, even if he manages to steal the password file. So that right there is using hashing to help with password storage. So let's summarize what we talked about. Hash functions take an arbitrary message and they compute a fixed length hash with it. And they have many applications in computer science, even outside of security. So don't be surprised if you see hashing in use in other areas of computing, but they're based on the same basic technology that we just talked about here. Thanks.